Late November 1943, Western Europe. The sky hung gray and heavy with the threat of winter storms, clouds stacked in layers from 8,000 feet to 25,000. The kind of weather that grounded most aircraft and turned fighter patrols into exercises in freezing misery. But slicing through that overcast at 27,000 feet, where the air was thin enough to make men gasp and cold enough to kill in minutes, came a formation of aircraft that didn't belong in any conventional understanding of fighter design. 6 silver machines, their twin booms gleaming even through the mist, their distinctive silhouettes unmistakable to anyone who had studied aircraft recognition charts. The Lockheed P-38 Lightning. The Americans called it their long-range escort. The British called it impressive but complex. The Germans called it der Gabelschwanz Teufel, the fork-tailed devil, and they said it with a mixture of mockery and grudging respect that betrayed deeper uncertainties about what they were facing. The sound reached the ground before the visual identification was possible. Not the single-throated roar of a conventional fighter, but something different, a harmonic hum created by counter-rotating propellers, each Allison V1710 engine spinning its 3-bladed prop in opposite directions to eliminate torque. The result was a sound signature unlike anything else in the sky, a mechanical symphony that German radio operators learned to recognize even through static and distance. When that sound appeared on the radio frequencies, Luftwaffe pilots knew the Americans were coming, and they knew the mission profile would be unlike the short-range sorties of Spitfires or the desperate defensive scrambles of Soviet fighters. The Lightning meant the Americans were going deep, staying long, and coming back for more. Below, near a hastily repaired Luftwaffe airfield outside Bordeaux, ground crews worked on a prize that had fallen into their hands 3 days earlier. A P-38J, damaged by flak over a rail yard near the Spanish border, had nursed its way west with one engine streaming coolant and the other running rough from ingested debris. The pilot, Lieutenant James Morrison from Oregon, had coaxed the aircraft across 60 miles of hostile territory before the failing engine finally seized. He'd bellied the Lightning into a plowed field with enough skill that the airframe remained largely intact, the twin booms bent but unbroken, the central nacelle crumpled but holding its secrets. Morrison was now a prisoner of war. His aircraft was about to become a classroom. German mechanics and engineers surrounded the wrecked Lightning like archaeologists examining an alien artifact. The twin-boom configuration seemed ungainly at first glance, a rejection of the elegant single-engine fighters that dominated European thinking. Why mount the engine so far from the fuselage? Why place the pilot in a nacelle between them instead of ahead of a nose-mounted engine? Why complicate everything with 2 of everything? 2 engines, 2 turbos, 2 sets of cooling systems, dual hydraulics. The initial reaction among Luftwaffe ground crews was dismissive. "Too complicated," a senior mechanic muttered to his assistants. "Americans always overcomplicate things. Look at their trucks, their radios. They think more parts means better engineering." His assistants laughed, nodding agreement. They had grown up in a technical culture that prized elegance and simplicity, that believed the best solutions were the most refined. But as they began stripping panels and exposing the Lightning's internal systems, the laughter faded, replaced by silence. Then by urgent conversations. Then by orders to transport the entire aircraft to Rechlin, the Luftwaffe's primary test center, where specialists could examine every component in detail, because what they were finding contradicted everything they thought they knew about American engineering. The complexity wasn't random. It was systematic. Every doubled component had a purpose. Every system integrated with others in ways that created capabilities no German fighter possessed. The Lightning wasn't just different. It was operating on principles that German aviation hadn't fully grasped. How could an aircraft they mocked end up defining the very limits of power? The P-38 Lightning emerged from requirements that seemed contradictory in 1937 when the U.S. Army Air Corps issued its specification for a new interceptor. The military wanted a fighter that could climb to 20,000 feet in 6 minutes, reach 360 miles per hour at altitude, maintain that speed for at least an hour, and carry heavy armament. These requirements were mutually exclusive with existing technology. Climb rate demanded power. Speed at altitude demanded streamlining. Endurance demanded fuel capacity that added weight. Heavy armament added more weight. No single engine design could satisfy all parameters simultaneously. So Lockheed's legendary designer Clarence Kelly Johnson, working in what would later become famous as the Skunk Works, proposed something radical: twin engines. The logic was simple but revolutionary. Two engines provided redundancy, critical for long-range operations where engine failure meant death over enemy territory. Two engines allowed the weight of armament to be concentrated in the central nacelle, where the pilot sat, eliminating the need for gun convergence and creating a cone of fire that extended hundreds of yards ahead of the aircraft. Two engines meant more power without requiring a single massive engine that would have been impossible to cool effectively. And two engines, mounted in streamlined booms that also housed the tail surfaces, created an aerodynamically clean design with surprisingly low drag despite its unconventional appearance. But the real innovation wasn't the twin-engine layout. It was what Lockheed did with those engines. Each Allison V1710 was mated to a General Electric Type B2 turbo-supercharger, a complex piece of machinery that used exhaust gases to drive a turbine that compressed intake air, maintaining sea-level pressure and power output at altitudes where normally aspirated engines would gasp and die. Turbo-supercharging wasn't new. It had been developed in the 1920s, but implementing it reliably on a fighter aircraft required solving thermal management problems that had defeated previous attempts. The turbos operated at temperatures exceeding 1,500 degrees Fahrenheit. The ducting had to route exhaust gases, compressed air, and coolant through the same narrow booms without any system interfering with the others. Lockheed engineers spent months designing intercoolers, heat exchangers, and ducting systems that could handle these thermal loads. They used exotic alloys for turbine housings. They calculated airflow patterns through cooling passages with precision that required advanced mathematics. They integrated everything into a package that fit within the Lightning's sleek booms while maintaining accessibility for maintenance. The result was an aircraft that could cruise at 25,000 feet, while its enemies struggled at 18,000, that could maintain full power where other fighters were running on thin air and desperation. The turbo-supercharger gave the P-38 a performance envelope that extended the battlefield vertically by thousands of feet. The armament installation was equally innovative. Traditional fighters mounted guns in the wings, which required harmonizing, adjusting each gun so all rounds converged at a specific range, typically 250 to 300 yards. This convergence meant that at any other range, the fire pattern spread out, reducing hit probability. The P-38 concentrated all armament in the nose, one Hispano 20mm cannon, and four Browning 50 caliber machine guns, all firing straight ahead, all controlled by a single trigger. The pilot aimed the aircraft, pressed the trigger, and everything fired in a tight cone that remained effective from point-blank range to over 1,000 yards. The psychological and tactical advantages were immense. Pilots didn't have to judge range for convergence. They pointed and fired, knowing their weapons would hit where they aimed. The Lightning entered combat in November 1942 during Operation Torch, the Allied invasion of North Africa. Early missions revealed teething problems that would plague the aircraft throughout its service life. At high speeds during dives, the P-38 experienced compressibility, a phenomenon where airflow over the wings approached the speed of sound, creating shock waves that made the controls lock up and the aircraft nearly uncontrollable. Pilots learned to avoid steep dives or use specialized dive flaps that disrupted airflow and prevented compressibility. The cockpit heating system was inadequate for high-altitude operations over Europe, leaving pilots freezing at 30,000 feet. The engines, while powerful, required careful management to avoid overheating in climbs or overcooling in descents. But for all its problems, the P-38 could do things no other Allied fighter could match in 1942 and early 1943. It had the range to escort bombers deep into enemy territory and return without refueling. Its armament could destroy heavy bombers with short bursts where other fighters had to make multiple passes. Its speed and climb rate at altitude made it nearly invulnerable to interception by German fighters that excelled at lower altitudes, and its twin-engine configuration provided survival margins that single-engine fighters couldn't offer. Pilots who lost an engine could often fly home on the remaining one, a feat impossible in a Spitfire or Mustang. German intelligence officers tracking Allied air operations noted the P-38's appearances with increasing concern. Early encounters in Tunisia showed it to be fast, but not particularly maneuverable at low altitude, where the extra weight and bulk penalized turn performance. Luftwaffe pilots learned to force P-38s down to the deck, where Bf-109s and FW-190s could turn inside them. But above 20,000 feet, the equation reversed. The Lightning's turbocharged engines maintained power while German fighters struggled. The P-38 could outclimb and out-accelerate anything the Luftwaffe fielded at altitude. And increasingly, That was where the war was being fought. At altitudes where American heavy bombers flew their missions, where the P-38s ranged ahead and behind and above the formations, killing any German fighter that tried to attack. By mid-1943, the Lightning's reputation among Luftwaffe pilots had evolved from dismissive mockery to wary respect. Intelligence reports compiled from prisoner interrogations revealed that German pilots referred to the P-38 as dangerous, fast, and difficult to engage successfully. The twin-boom configuration made it easy to identify at a distance, which allowed German pilots to avoid combat if they chose. But the same visibility also advertised American reach. When P-38s appeared over targets deep in Germany, targets that had been beyond Allied fighter range just months earlier, the psychological impact was profound. The sky wasn't safe anymore. The Americans could go anywhere. The technical intelligence community within the Luftwaffe understood that the P-38 represented something more significant than just another fighter design. It represented a different approach to aircraft engineering, one that embraced complexity to achieve capabilities that simpler designs couldn't match. German fighters were generally lighter, more agile, optimized for the kind of dogfighting that had characterized the Battle of Britain and the Eastern Front. They were beautiful aircraft in their way, elegant and refined. But they were short-legged. A Bf-109 had an effective combat radius of perhaps 200 miles. An FW-190 was even shorter. They were defensive weapons, designed to intercept bombers and fight over friendly territory, where damaged aircraft could reach bases and pilots could be recovered if shot down. The P-38 was an offensive weapon. Its combat radius exceeded 500 miles with external tanks, enough to escort bombers from England to Berlin and back. This range translated into strategic flexibility that German fighters couldn't counter. The Lightning didn't have to engage in dogfights. It could choose when and where to fight, could disengage at will using its superior speed at altitude, could hunt lone German fighters while avoiding unfavorable situations. This tactical freedom was perhaps more valuable than any performance advantage. German pilots increasingly found themselves reacting to American initiatives rather than dictating the terms of engagement. The captured Lightning near Bordeaux represented an opportunity to understand this technical and tactical superiority at a granular level. Luftwaffe technical intelligence had examined wrecked P-38s before, but most had been too damaged to yield useful information. Crashed fighters burn or break apart. Components scatter, critical systems are destroyed. But Lieutenant Morrison's forced landing had been almost gentle by the standards of aerial combat. The airframe was bent but structurally intact. The engines were damaged but their internal components could be examined. The electronics, cooling systems, hydraulics, and flight controls were largely functional. German engineers could not only study the Lightning's design, but understand how all the systems integrated into a functioning whole. December 1943. Rechlin Lehrz, Airfield, Germany. The captured P-38J sat in a massive hangar under Klieg lights that made the aluminum skin gleam like polished silver. Teams of Luftwaffe engineers, Messerschmitt designers, and RLM technical inspectors surrounded the aircraft, notebooks in hand, cameras ready, measurement tools laid out with Teutonic precision. The directive from Berlin was explicit. Determine what makes this aircraft capable of performances our intelligence reports claim, but our aviation theory suggests should be impossible. Determine whether American engineering has achieved a breakthrough or whether they've simply built an overcomplicated monster that will prove unsustainable in mass production. The initial walk-around reinforced existing prejudices. The Lightning was large for a fighter, with a wingspan of 52 feet and a length of 37 feet including the twin booms. Empty weight exceeded 12,000 pounds, nearly double that of a Bf-109. The landing gear was robust but added weight and complexity. Everything about the design seemed to violate the German principle of fighting weight. One engineer commented that it looked more like a light bomber than a fighter. Another noted that the twin-boom configuration would be hideously difficult to manufacture in quantity, requiring jigs and tooling that would exceed the cost of producing two conventional fighters. The American industrial capacity might absorb such costs, but for Germany, already straining under resource shortages, it seemed wasteful. Then they opened the panels, started tracing systems, examined components under magnification, and the prejudices began cracking like ice under pressure. The turbo-supercharger installation revealed itself as a masterpiece of thermal engineering. Each boom housed a complete propulsion system: engine, reduction gearbox, turbocharger, intercooler, oil cooler, radiator, ducting for intake and exhaust, fuel lines, electrical systems, and controls. All of it packaged into a streamlined nacelle that created minimal drag while maintaining accessibility for maintenance. The turbos themselves were manufactured to tolerances that exceeded German production capabilities for non-critical components. The turbine wheels were balanced to micron precision. The heat-resistant alloys showed sophisticated metallurgy. More importantly, the entire system was designed for reliability under combat stress. Redundant sensors monitored temperatures, pressures, and RPMs. Automatic controls regulated boost pressure and fuel mixture. If one system failed, the other engine could maintain flight. The level of systems integration was unlike anything in Luftwaffe service. German fighters relied heavily on pilot skill to manage engine operations. Bf 109 pilots had to manually adjust propeller pitch, throttle, mixture, and supercharger settings to optimize performance at different altitudes. A skilled pilot could extract remarkable performance. An inexperienced pilot would overheat the engine or overboost and destroy it. The Lightning automated much of this complexity, allowing pilots to focus on tactics rather than engine management. The electrical systems inspection yielded more surprises. American aircraft used 24-volt electrical systems compared to the 12-volt systems common in German designs. The higher voltage allowed lighter wiring and more powerful accessories. The radio equipment was compact, crystal-controlled for frequency stability, and capable of ranges exceeding 200 miles for air-to-air communication. German pilots were lucky to get 50 miles from their radios, and frequency drift was a constant problem. The Americans had integrated radio navigation, identification, friend or foe, IFF, transponders, and even provisions for future radar installations into a package that weighed less than comparable German equipment. The armament installation drew particular attention. German fighters typically mounted guns in wings or engine cowlings, both locations that required compromises. Wing-mounted guns needed convergence adjustment and suffered from dispersion at ranges beyond the convergence point. Cowling-mounted guns were limited by the need to fire through the propeller arc, requiring synchronization gear that reduced rate of fire. The P-38's nose armament avoided all these problems. The 20mm cannon was mounted centrally with 150 rounds of ammunition. The 450 caliber machine guns flanked it, each with 500 rounds. All 5 weapons fired straight ahead with no convergence needed. The sight picture was simple. Put the reticle on target, press trigger, watch target disintegrate. Test firing the captured guns, using ammunition salvaged from other wrecks, demonstrated the system's effectiveness. The concentration of fire was devastating. A 1-second burst from all 5 guns put over 100 rounds into a target area, roughly 6 feet in diameter at 500 yards. A 2-second burst was sufficient to destroy any fighter or cripple a heavy bomber. German pilots typically needed multiple passes to bring down American 4-engine bombers. A P-38 could do it in one pass if the pilot aimed well. This firepower advantage translated into higher kill rates and lower exposure time, both critical factors in the mathematics of air combat survival. The Allison engines themselves revealed American production sophistication. Each V-1710 displaced 1,710 cubic inches and produced 1,425 horsepower at war emergency power. The construction quality was remarkable. Cylinder machining showed tolerances measured in 10,000ths of an inch. Crankshafts were nitrided for hardness and fatigue resistance. Pistons used aluminum alloys with silicon to reduce thermal expansion. Valves were sodium-cooled for temperature management. The Germans understood all these techniques in theory, but implementing them at mass production scale, maintaining quality across thousands of engines, ensuring interchangeability of parts, this exceeded German industrial capabilities by 1943. More disturbing was the maintenance philosophy embedded in the design. German aircraft were built for skilled mechanics, working with comprehensive tooling at established airbases. Field repairs required expertise and time. The P-38 was designed for field maintenance by less skilled personnel using basic tools. Panels were standardized. Access points were logically positioned. Major components like engines could be changed in hours using portable hoists. The Americans had designed their aircraft for the reality of air war, that maintenance would happen in improvised conditions, that mechanics would be trained but not master craftsmen, that turnaround time mattered as much as performance. Rechlin's test pilots took the repaired Lightning up on 3 occasions before concerns about airframe integrity grounded further flights. The first flight was simply a verification that the aircraft could fly with makeshift repairs. The second focused on handling characteristics, how the P-38 responded to control inputs, how it behaved at various speeds and altitudes, what its stall characteristics were. The third was a performance evaluation, pushing the Lightning through maneuvers to assess its capabilities. The test reports filed by Luftwaffe pilots were remarkably honest. The P-38 was not a dogfighter. It couldn't turn with a Bf-109 or roll with an FW-190 at low altitude. The controls became heavy above 350 miles per hour, requiring significant strength to input commands. But above 25,000 feet, the equation changed. The turbocharged engines maintained full power where German fighters were struggling. The P-38 climbed like a rocket, accelerated smoothly, and maintained energy in maneuvers that would have bled speed from conventional fighters. One test pilot wrote, "At altitude, it is formidable. We have nothing that matches its high-altitude performance envelope." The dive characteristics produced mixed reactions. With dive flaps deployed, the P-38 could dive steeply without entering compressibility. But the dive acceleration was limited compared to German fighters, which could achieve higher terminal velocities. This meant a P-38 couldn't always escape by diving, a favorite German tactic when outnumbered. But it also meant the Lightning was more controllable during high-speed maneuvers. The test pilots noted that in combat, they would choose to engage P-38s at low altitude, where German fighters had advantages, and avoid combat above 20,000 feet where the Lightning dominated. The final technical assessment, compiled from dozens of specialist reports and signed by senior RLM officials, concluded with language that was carefully diplomatic, but fundamentally damning for German aviation industry assumptions. The P-38 Lightning was described as a highly sophisticated weapons platform that integrates advanced propulsion, systems automation, and concentrated armament into an effective long-range fighter. While exhibiting handling characteristics unsuitable for close-in dogfighting, it excels at high-altitude interception and escort missions. German industry currently lacks the production capacity and specialized components to replicate key systems, particularly turbo-supercharging at this scale. That last sentence was the critical admission. Germany could design systems like the P-38. German engineers understood the principles. But they couldn't build them in quantity while maintaining quality, couldn't integrate them into airframes while keeping costs manageable, couldn't support them in the field with available logistics. The Americans had solved problems that Germans understood existed, but hadn't prioritized. And now those solutions were escorting bombers over Berlin. The psychological impact of the Rechlin evaluation rippled through Luftwaffe command faster than the official reports could be distributed. Officers who saw the captured Lightning or read preliminary assessments understood immediately that the technical gap between American and German aviation had widened beyond what propaganda admitted. The implications were strategic and operational. If the Americans could field fighters with 500-mile combat radius, no target in Germany was beyond their reach. Luftwaffe defensive planning had assumed that certain industrial areas in eastern and southern Germany were safe from escorted bomber raids. The P-38 invalidated those assumptions. Fighter units operating against American bomber streams began reporting increased P-38 encounters throughout winter 1943-44. The Lightnings typically flew top cover above the bomber formations, positioned to dive on German fighters attempting to attack from above, the standard Luftwaffe tactic for avoiding defensive fire from bomber gunners. This forced German fighters to attack from below or beam on, both less effective approaches that exposed them to longer periods under defensive fire. Intercept effectiveness declined measurably. Where German fighters had been achieving kill ratios of 3 or 4 bombers destroyed per fighter lost in 1943, by early 1944, that ratio had fallen to nearly 1-to-1. The captured Lightning also became a propaganda problem. Luftwaffe public information officers had spent months portraying American aircraft as inferior, designed by engineers who prioritized comfort and ease of production over combat effectiveness. The narrative was that German fighters were technically superior, piloted by more experienced aviators, and that any setbacks were purely numerical. But pilots returning from missions over Germany told different stories. They described American fighters that could outperform German designs at critical altitudes, that had radios that actually worked reliably, that could fly home on one engine when a Bf-109 or FW-190 would have been a glider. German aircraft designers responded to the Lightning with a mixture of professional admiration and strategic despair. Messerschmitts engineers studied the turbo-supercharger installation and concluded that developing a similar system for the Bf-109 would require redesigning the airframe from scratch, effectively creating a new aircraft. Focke-Wulfs investigated turbocharging for the FW-190, but encountered metallurgical problems with turbine materials that couldn't be solved with available alloys. Both companies proposed advanced designs incorporating lessons from the P-38. But by late 1943, German industry was already committed to jet aircraft development. Resources that might have gone to incremental improvements of existing designs were being diverted to revolutionary projects like the Me-262. This strategic choice, betting on jets rather than improving conventional fighters, was influenced partially by the recognition that conventional German fighter technology couldn't catch American aviation engineering in the near term. The P-38 demonstrated that American industry could implement complex systems at scale while maintaining quality. German industry, increasingly bombed, resource-constrained, and dependent on forced labor, was struggling to maintain production of existing designs. Developing new conventional fighters to match American capabilities seemed futile. Better to leapfrog with jets, if they could be made operational before the war was lost. For American strategic planning, intelligence reports about German examination of captured P-38s provided useful insights into enemy technical capabilities and limitations. The fact that Germans focused so intensely on the turbo-supercharger system indicated they understood its importance but lacked the ability to replicate it. This suggested that American fighters operating at high altitude would continue to have performance advantages. It also validated the strategic decision to develop long-range escorts for bomber operations. If the Germans respected the P-38's capabilities enough to study captured examples in detail, the aircraft was achieving its intended effect. P-38 production accelerated throughout 1944. Lockheed's Burbank plant was producing over 300 Lightnings per month at peak output. The aircraft served in every theater, escorting bombers over Germany, flying reconnaissance over Italy, supporting island-hopping operations in the Pacific, hunting U-boats over the Atlantic. Some of the war's most successful American aces flew P-38s, including Richard Bong with 40 kills and Thomas Maguire with 38. The Lightning became synonymous with American long-range air power, visible proof that American industry could design, build, and deploy sophisticated weapon systems at scales the Axis couldn't match. The Germans never developed an effective counter to the P-38's high-altitude performance. Attempts to field specialized high-altitude interceptors like the FW-190D9 and TA-152 came too late and in too few numbers to matter strategically. By mid-1944, the Luftwaffe was fighting a defensive war with declining resources, diminishing pilot experience levels, and fuel shortages that limited training and operations. The technical advantages that German fighters might have possessed in dogfights at 15,000 feet were irrelevant when they couldn't reach combat altitude or had to disengage to conserve fuel. The evaluation of the captured Lightning at Rechlin became a case study in the difference between understanding and capability. German engineers understood everything about the P-38. They could see how it worked, why it worked, what advantages its design provided. But understanding didn't translate into replication. The turbo-superchargers required alloys Germany couldn't produce in sufficient quantities. The electrical systems required manufacturing precision that German industry couldn't maintain under bombing. The armament concentration required design philosophies that German air doctrine hadn't embraced. Knowledge without capability is just frustration. American pilots flying P-38s over Europe in 1944 sometimes encountered German fighters with unusual markings, captured Allied aircraft being evaluated or used for training. Occasionally, rumors circulated about Lightnings in Luftwaffe colors being used to infiltrate American formations. These rumors were mostly fantasy. The Germans never made the captured P-38s operationally useful. They were study specimens, teaching aids that told German engineers what they were up against. Every hour German technicians spent examining American aircraft was an hour proving that the technical gap was real and widening. The P-38 Lightning represented the first generation of what would eventually be called systems aircraft, platforms where the integration of multiple complex systems created capabilities exceeding the sum of individual components. The concept seems obvious in retrospect, but in the early 1940s it was revolutionary. Most fighters were built around an engine, with everything else treated as secondary. The Lightning was built around a mission profile, long-range escort, with every component optimized to support that mission. This design philosophy would dominate American aviation for decades. The turbo-supercharger technology pioneered on the P-38 at scale directly influenced subsequent American designs. The Republic P-47. Thunderbolt used a massive turbo-supercharger installation that gave it even better high-altitude performance than the Lightning. The Boeing B-29 Superfortress used turbocharged Wright R-3350 engines to cruise at 30,000 feet, above the reach of most Japanese fighters and anti-aircraft guns. Post-war, turbocharging evolved into jet engine compressors, the same basic principle of using exhaust energy to compress intake air, just implemented differently. The electrical systems integration on the P-38 established standards that became universal in American military aviation. The 24-volt electrical system, crystal-controlled radios, IFF transponders, and provisions for radar, all of these became baseline requirements for subsequent designs. By war's end, American fighters routinely carried electronics that would have seemed like science fiction in 1940. The Lightning was the platform where many of these technologies were first integrated successfully, where engineers learned which approaches worked and which didn't. The nose armament concept influenced jet fighter design in the 1950s and beyond. Most early jets mounted guns in the nose for the same reasons the P-38 did: concentration of fire, no convergence issues, simplified aiming. The F-86 Sabre, F-100 Super Sabre, and virtually every American jet fighter through the F-4 Phantom followed this layout. Even when missiles became primary weapons, the nose remained the preferred location for auxiliary guns. The P-38's designers had established a pattern that proved enduringly effective. The manufacturing techniques developed for Lightning production had broader implications for American aerospace industry. The twin-boom configuration required sophisticated jigs and tooling to maintain alignment and structural integrity. Lockheed developed assembly processes that allowed multiple work crews to build different sections simultaneously, then mate them with precision. These parallel production methods reduced manufacturing time and increased output. Post-war, similar techniques enabled the rapid expansion of commercial aviation, where Lockheed became a dominant manufacturer of airliners using organizational skills refined during wartime fighter production. The strategic lessons were equally important. The P-38 demonstrated that range mattered more than most performance parameters. An aircraft that could reach the target, fight effectively, and return home was more valuable than one with superior dogfighting characteristics but insufficient range. This realization drove American strategic bomber escort doctrine, influenced post-war fighter design, and eventually led to the development of air-to-air refueling as standard practice. The Lightning taught the U.S. Air Force that controlling distance controlled options, and options won wars. German aviation never fully internalized these lessons, partly because their strategic situation didn't allow it. Defending Germany required interceptors that could scramble quickly, climb fast, and kill bombers efficiently. Range was less critical when you were fighting over your own territory. But this defensive mindset trapped German aviation in a reactive posture, always responding to American initiatives rather than dictating terms. The P-38 was an offensive weapon in an offensive air campaign. German fighters were defensive weapons in a losing war. The comparison between American and German production philosophies revealed itself in maintenance and sustainability metrics. P-38 squadrons maintained operational readiness rates above 70% throughout most of the war. German fighter units struggled to keep 50% of their aircraft operational by 1944. The difference wasn't pilot skill or initial quality. It was systems design that considered field maintenance, spare parts logistics, and repair procedures as integral to combat effectiveness. German aircraft were engineering marvels when factory fresh. American aircraft were designed to stay operational under field conditions, with minimal specialized support. The post-war aerospace industry inherited direct technological lineage from the P-38. Lockheed's experience with turbo-supercharging, high-altitude flight, and systems integration led directly to the P-80 Shooting Star, America's first operational jet fighter. Many engineers who worked on the Lightning continued at Lockheed through the jet age, bringing institutional knowledge that influenced designs for decades. Kelly Johnson, the P-38's primary designer, went on to create the U-2 spy plane, the SR-71 Blackbird, and numerous other classified aircraft. The Lightning was his first major success, the foundation of a career that revolutionized aviation. The Germans, despite their thorough study of the captured P-38, never developed equivalent capabilities because they lacked the industrial infrastructure and resource access that American aviation industry enjoyed. This wasn't a failure of German engineering skill. Their engineers understood the principles as well as anyone. It was a failure of industrial capacity and strategic resource allocation. By the time they understood what the Americans had achieved, it was too late to respond effectively within conventional aviation technology. The jet programs consumed resources that might have gone to closing the gap, and the jets, while technically impressive, arrived too late and in too few numbers to alter the war's outcome. In the end, the laughter died in the technical specifications. The German mechanics who first examined the wrecked P-38 near Bordeaux, who had joked about American over-engineering and unnecessary complexity, fell silent as they traced systems that revealed a nation's industrial philosophy rendered in aluminum and steel. The fork-tailed devil had turned from punchline to prophecy. What they had dismissed as ungainly was actually sophisticated. What they had labeled over-complicated was systematically redundant. What they had mocked as typical American excess was, in fact, the application of manufacturing abundance to achieve combat capabilities that simpler designs couldn't match. The captured Lightning at Rechlin became more than a technical intelligence asset. It became a mirror that reflected Germany's industrial limitations back at engineers who had believed their technical education and design elegance would overcome material disadvantages. Every turbo-supercharger they examined, every electrical system they traced, every armament installation they measured told the same story. American industry could build complexity at scale. German industry, for all its theoretical knowledge and skilled workforce, could not. Not under wartime conditions. Not with resources stretched across multiple fronts. Not with factories being bombed and supply chains disrupted. The P-38 pilots who flew missions over Germany in 1944 and 1945 rarely knew about the captured aircraft being studied at Rechlin. They knew their own experiences, the reliable hum of counter-rotating propellers, the confidence that came from concentrated nose armament, the security of twin engines when one got hit, the satisfaction of escorting bombers deep into enemy territory and bringing them home. They knew that German fighters avoided them when possible, that the once feared Luftwaffe was increasingly absent from skies that should have been contested desperately. They knew that something had shifted in the balance of air power, that American reach now extended anywhere American strategy required. History records what the Germans eventually admitted in technical reports and post-war interviews, in the careful language of engineers who had studied an enemy weapon and found it superior in the ways that mattered most. They had never seen power like that, not brute horsepower, though the Lightning had plenty, but systematic power, the power of industrial organization that could design complexity, manufacture it reliably, distribute it globally, and maintain it under combat conditions. The power of an economy that could afford to build fighters with two engines when others struggled to produce enough single-engine designs. The power of engineering philosophy that embraced redundancy and systems integration rather than minimalist elegance. The P-38 Lightning flew its last combat missions in August 1945, as the war ended with Japanese surrender. Many Lightnings were scrapped immediately after the war, cut apart for aluminum recycling, or pushed into the sea from aircraft carriers clearing their decks for peacetime operations. Some were sold as surplus, finding second lives as racing planes or private aircraft for wealthy enthusiasts. A handful were preserved in museums, their twin booms and central nacelles restored to wartime configuration, standing testament to an era when American aviation engineering took risks that paid off in combat effectiveness. The pilots who flew them carried memories that time couldn't erase, the sound of those counter-rotating propellers, the feel of the control yoke at altitude, where thin air made every input feel sluggish but effective. The sight of German fighters breaking away rather than engaging, recognition that the Lightning had earned respect through performance. Some pilots loved the aircraft, praised its capabilities, and mourned when they transitioned to other types. Others acknowledged its limitations, the heavy controls at high speed, the lack of maneuverability at low altitude, the complexity that sometimes created maintenance headaches. But even the critics admitted that the Lightning did what it was designed to do: extend American fighter coverage to ranges that changed the strategic equation of the air war. The Germans who examined the captured P-38 at Rechlin scattered to various fates as the war ended. Some continued in aviation engineering in post-war Germany, working on commercial aircraft or consulting for emerging aerospace companies. Others emigrated, bringing their skills to American or British industry, contributing to the jet age they had glimpsed through captured examples of Allied technology. Their detailed reports on the Lightning, meticulously compiled with German thoroughness, survived in archives where historians later found them, technical documentation of the moment when one nation's engineering philosophy confronted another's and found itself wanting. The strategic lesson transcended the specific aircraft. The P-38 demonstrated that in modern warfare, particularly air warfare, the ability to design and produce sophisticated systems at scale mattered more than incremental advantages in traditional performance parameters. An aircraft that could reach targets, accomplish missions, and return reliably was worth more than one with superior dogfighting characteristics but limited range or availability. This lesson influenced post-war American military procurement for decades, establishing patterns where capability and sustainability were valued over peak performance, achieved at the cost of complexity or producibility. The Lightning's legacy lives in the aircraft that followed it, in the design philosophies it validated, in the strategic concepts it proved viable. The long-range fighter escort became a cornerstone of American air doctrine. Systems integration became the standard approach to military aviation design. Turbo-supercharging evolved into the jet engines that powered the next generation of fighters. The twin-boom configuration reappeared in designs like the P-61 Black Widow, the OV-10 Bronco, and various experimental aircraft. Each time, designers referenced the P-38 as proof that unconventional layouts could work if executed with sufficient engineering rigor. But perhaps the most enduring legacy is simpler and more profound. The P-38 Lightning proved that American industrial capacity, when properly directed and adequately resourced, could solve problems that seemed intractable to others. The Germans studied the captured aircraft and learned what they were facing. Not just a weapon, but a system. Not just design innovation, but production excellence. Not just one aircraft, but the leading edge of an industrial avalanche that would bury the Axis under tonnage of steel, oceans of fuel, and formations of aircraft that darkened the skies. When the Germans laughed at the fork-tailed devil in 1942, they were laughing at a concept they didn't understand. When they stopped laughing in 1943, having examined the reality of American engineering, it was too late to respond effectively. The war had become a contest of industrial systems, and in that contest, the nation that could build P-38 Lightnings by the thousands while equipping them with electronics, armament, and engines that each represented sophisticated manufacturing achievements, that nation was going to win. If a single captured Lightning could teach the enemy more about American capability than months of propaganda, what could an entire generation of American innovation achieve? The P-38 was the question. The answer came in the form of victory achieved through technology, industry, and the systematic application of engineering excellence to the problems of modern warfare. Subscribe to WWW2 Secret Archives to discover more hidden systems, forgotten machines, and the engineering breakthroughs that transform skepticism into dominance. The next story reveals another moment when innovation met doubt and emerged triumphant.